Hi everyone. So today we are going to discuss a very important theorem, that is a Cauchy criterion for uniform convergence of a series of functions. So when we discuss any result of series, always we first consider a sequence of partial sum. So here also I will consider a sequence of partial sum first. So here also I have considered let Sn be a sequence of partial sum of series summation Fn. Instead of Fn, I will consider summation Fk, since in example also, in the statement also, they have given summation Fk. Okay, so this is nothing but, this is nothing but Sn is equal to F1 plus F2 plus and so on Fk. Okay, so now if and only if part is there. Okay, if and only if. That means we have to assume first part, we have to prove second. After that, we have to assume second part, and we will prove first part. So let us consider the first part. I will consider series summation Fk converges uniformly on S. Assume that series summation Fk converges uniformly on S. See, when we say the series converges, that means this corresponding sequence of partial sum also converges. Therefore, we can say Sn of x is also converges uniformly on S. See, if Sn converges uniformly, you can say it is uniformly Cauchy, since every uniformly convergent sequence is uniformly Cauchy. Therefore, sequence Sn is uniformly Cauchy on S. Instead of Sn, we will call it as Sk. We'll call it as Sk. Now we will take epsilon greater than 0, since we have to prove for given epsilon. So here also I will consider let epsilon greater than 0 be given. So now I will use this definition of uniformly Cauchy sequence. So Cauchy sequence, therefore we can say there exists n naught belongs to set of natural number such that mod Sn of x minus Sm of x less than epsilon for all m greater than n greater than or equal to n naught. As it is uniformly Cauchy, we can say this is true for all x belongs to capital S. Okay, so now I will put the value of Sm of x. What is Sm of x? See, what is Sm of x? Sk means f1, f2 up to so on fk. So Sm is obviously f1, f2 and so on fm. See, I wrote the value of Sm of x. As n is less than m, so that's why we can, when you write f1 to fm, there will be fn between them. Okay. So after that, what will I do? Minus, I will put the value of Sn of x. Sn of s is obviously f1, f2 plus and so on fn. And this is less than epsilon. So this is less than epsilon. So I can write here less than epsilon. See, guess now what will happen next? Obviously, f1 of x will get cancelled with this f1 since minus sign is there. f2 of x will get cancelled with f2 and so on. fn of x will get cancelled with this fn of x. Okay, so see, therefore we get, I wrote the remaining terms, fn plus 1 of x f up to fm of x, which is less than epsilon. Now we need to carry this condition for all m greater than n greater than or equal to n naught, and for all x belongs to capital S. Okay, so yeah, I will write the same thing in form of summation now. Okay, in a form of summation. So therefore, summation. So now k running from where to where? N plus 1 to m fk of x less than epsilon. Now simply we have to carry this condition for all m greater than n greater than or equal to n naught, and for all x belongs to S. Okay, so in this way we have done the half part of the theorem. Okay, still remaining half is remaining. Okay, see, now we will consider its reverse pass. I will consider this converse part. Now I will consider this mod, and we have to prove that summation fk converges uniformly on S. Conversely, assume that for given epsilon greater than 0, there exists n naught belongs to set of natural number such that mod summation k running from n plus 1 to m Fk of x less than epsilon for m greater than n greater than or equal to n naught and for all x belongs to S. Okay, so now to prove that summation Fk converges uniformly on S. Okay, so now to prove this thing, I will take epsilon greater than 0 be given. Okay, so by now I can use this our assumption, what we assume. So for the given epsilon there exists n naught, so that thing I will write now. By our assumption there exists n naught belongs to set of natural number such that mod summation k running from n plus 1 to m Fk of x less than epsilon for all m greater than n greater than or equal to n naught and for all x belongs to capital S. So now I will split this summation. Okay, this summation, so see k varies from n plus 1 to m, so therefore we can write fn plus 1 plus fn plus 2 plus and so on fm less than epsilon. Okay, so see same thing we can write it as same thing we can write. Okay, so what I have done, what is the difference between the previous step and this step? So we have considered this n terms additionally, f1 f2 and so on fn. So obviously I need to subtract, then only it will get managed. Okay, so see, so f1 will get cancelled, f2 will get cancelled and fn will get cancelled because of they have opposite signs, and you will have fn plus 1 to fm and you will have a previous step. Okay, so yeah, now tell me f1 f2 and so on we are adding up to fm now. So this is nothing but, yeah, we have seen the definition of fk is sk is nothing but we add first k terms, right? So what we are doing, we are adding first m terms, so that's why this is nothing but sm of x, and f1 f2 up to fn, this is nothing but sn of x, which is less than epsilon. Okay, it's just I need to carry this condition here. Okay, so tell me, this is definition of what? Mod Sm minus Sn less than epsilon. Is this a definition of Cauchy sequence? Yeah, of course, this is a definition of Cauchy sequence. So that's why we can declare Sk is a uniformly Cauchy. Why I'm saying it is uniformly Cauchy? Because this is true for all x belongs to S. So I can say Fk is uniformly Cauchy on S. As it is uniformly Cauchy, you can say it is uniformly convergent on S. Therefore, Sk of x is uniformly convergent on S. As sequence of partial sum convergent, we can say the corresponding series also convergent. Therefore, the given series summation Fk is also uniformly convergent on S. Okay, so converse part is also done. Okay, hence the theorem. Thank you.